At first, the movement seemed natural, a smooth arc, a harmless trajectory. But on the morning of January 4th, the arc changed, slightly, subtly, but unmistakably. It was the kind of change that doesn't come from chaos, but from control. 3I Atlas, the third confirmed interstellar object to enter our solar system, is no stranger to anomalies. It's been pulsing, redirecting jets, reflecting light when it shouldn't, and generating power in ways no comet ever has. But now, it's near Jupiter, and its trajectory just shifted again. Not away from the planet, but toward it. Some believe this is routine, a comet taking a common turn near a gas giant. But the data doesn't agree. This isn't a gravitational curve, it's something more exact, more complex, more like a maneuver. So today, we ask a question that once belonged only to science fiction. What if 3I Atlas isn't passing by Jupiter? What if it's using it? And if so, what for? Let's explore what just changed, and why Jupiter may not be a detour but a slingshot. From the moment it entered our solar system, 3I Atlas was different. But until now, its trajectory had been predictable, hyperbolic, inbound, untouched by the pull of any planet. It coasted through deep space on a path no comet from our system could ever take. Fast, clean, silent. Its curve was precise, consistent with Newtonian expectations. Until the morning of January 4th. That's when the arc began to shift. At first, the change was microscopic, a tiny deviation in telemetry logged by tracking software at the Jet Propulsion Laboratory. It was so small, in fact, that the first analysts marked it as noise, perhaps a processing lag, perhaps a calibration error in ground-based observatories. But the next day, the same deviation appeared again, not just in one model, in 3. It was a change in heading, subtle yet consistent across multiple observations. From Hawaii to Chile, optical readings began to register a drift in right ascension. The object, which had been coasting steadily, now seemed to be adjusting, curving just slightly inward toward Jupiter's gravitational domain. That wasn't supposed to happen. Jupiter's gravitational field is vast, but the kind of slingshot effect that influences a comet's motion typically occurs only when the object enters what scientists call the planet's Hill sphere, a region of space where the planet's gravity dominates over the sun's. 3I Atlas wasn't there yet. It was still over 20 million kilometers away, far outside the region where passive gravitational pull should have any measurable effect. So how then did its path begin to bend? Gravitational pull isn't magic. It has rules. Distance matters, mass matters, velocity matters, and the math, at least the math we've known for centuries, didn't support what we were seeing. The deviation was too early, the bend was too exact, and the curvature didn't behave like a passive response. It looked like alignment. Trajectory simulations showed that 3I Atlas wasn't being tugged accidentally. It was positioning itself deliberately, the way a spacecraft would if it were preparing for a gravitational assist. Not because it had to, but because it wanted to. If you've ever watched the flight path of a probe like Cassini or Voyager 1, you know the pattern. A slow curve begins before the planetary encounter, a pre-maneuver, a calculated lead-in, a signal that the object isn't drifting, it's navigating. That's what analysts now believe we're watching. 3I Atlas isn't turning because it's being pulled, it's turning because it's planning ahead. The angle of descent toward Jupiter's gravity well is precise. Within half a degree of the optimal vector used in spacecraft slingshot missions, it's threading a needle, one that no ordinary comet has ever threaded so cleanly. What's more, the telemetry doesn't show instability, no wobble, no sublimation-induced jetting, no rotation inconsistencies, just one continuous measured arc, smooth, almost silent, almost designed. And this change in direction, though small, it may be the most important moment in the entire observation campaign, because it introduces intent, and intent changes everything. If 3I Atlas is using Jupiter not as an obstacle, but as a tool, that means it's not just a visitor, it's a traveller, and travellers, unlike debris, have destinations. This is no longer a question of what it is. Comet, probe, anomaly. It's a question of what it's doing, and for the first time, we're watching it do something. Before we try to understand what 3I Atlas might be doing near Jupiter, we need to understand the principle it now appears to be using. The gravitational slingshot, also known as a gravity assist, is one of the most elegant maneuvers in celestial mechanics. It doesn't require rockets or fuel, it only requires precision. Here's how it works. When a spacecraft approaches a planet, it falls into the planet's gravitational field. From the perspective of the spacecraft, it speeds up as it moves closer, pulled by the gravity of the planet, and slows down again as it leaves, just like a roller coaster cresting and descending a hill. To a casual observer, it might seem like nothing has changed. In fact, if you measure only the spacecraft's speed relative to the planet, it leaves with the same speed it entered. But in space, context matters. What really changes is the spacecraft's velocity relative to the Sun. If the spacecraft approaches the planet from behind, in the direction the planet is moving around the Sun, it effectively steals a tiny fraction of the planet's orbital momentum. That momentum adds to the spacecraft's own motion, accelerating it forward and altering its trajectory outward into space. The planet slows down by an imperceptible amount, and the spacecraft gains speed. No fuel, no engine, just gravity and timing. This technique has been used by nearly every deep space probe humanity has launched. Voyager 1 used a gravity assist from Jupiter to propel itself towards Saturn, and then another from Saturn to escape the solar system entirely. Cassini used multiple assists to settle into orbit around Saturn. Even modern missions like ESA's JUICE and NASA's Europa Clipper rely on slingshots for energy-efficient travel. But here's the crucial part. These assists only work if the spacecraft approaches at exactly the right angle. Too steep and the object crashes or gets captured. Too shallow and it simply skims past, missing the assist entirely. For a successful slingshot, the spacecraft must approach with sub-degree accuracy. The timing must be precise. The curvature must be calculated. It's not something a natural object usually achieves. Comets, real ones, almost never slingshot. They don't care about efficiency. They don't plan trajectories. They follow chaotic, sun-dominated paths, shedding gas and dust, tumbling as they go. They respond to heat, to pressure, to randomness. They don't steer into gravity wells for momentum. They get pulled in by accident. But that's not what's happening with 3i Atlas. Its current trajectory doesn't look like it's being passively tugged. It looks like it's using Jupiter. The angle is perfect. The velocity matches the requirements for assist. And the curve, which began forming days before gravitational capture, suggests foresight. It suggests planning. If 3i Atlas were a probe, and we're not saying it is, only asking the question, this is exactly how it would execute a maneuver to gain speed. It would enter Jupiter's gravity well on a shallow inbound arc, rotate subtly to maintain orientation, dip just close enough to harvest momentum, and then slingshot outward toward a new destination. No visible propulsion, no fire, just a clean, invisible boost and departure. And that's the possibility scientists are now modelling. Not because it's the likeliest explanation, but because the physics leave no easy alternative. Whatever 3i Atlas is doing, it's not losing energy, it's gaining it. And in orbital mechanics, that kind of gain is never free, unless you're borrowing it from something massive, like Jupiter. Let's slow things down for a moment. If 3i Atlas were just a comet, a natural body composed of rock, dust and volatile ices, what would we expect it to be doing right now, near Jupiter? The answer begins with understanding what comets are. In our solar system, comets are the remnants of formation, primordial leftovers from the early protoplanetary disk. They typically reside in the cold outskirts, the Kuiper belt, and beyond that, the Oort cloud. These icy bodies remain frozen for billions of years until some gravitational nudge sends them tumbling inward, toward the Sun. As they approach, solar heat begins to work on them. The ice sublimates, turning directly into gas, and this gas carries tiny particles of dust with it, creating a visible coma around the nucleus. The pressure from sunlight and the solar wind pushes this material outward, forming the comet's famous tail, which always points away from the Sun, no matter which direction the comet is moving. But this process is not gentle. It's chaotic. Comets don't warm evenly. Their surfaces are irregular, often fractured, filled with pits and cliffs. The sublimation doesn't happen smoothly. It bursts. It vents. It rips material from the surface in unpredictable jets. And these jets aren't symmetrical. They twist the object's motion. They induce tumbling, spinning, even fragmentation. It's not unusual for a comet to split in half, or more, simply from the thermal stress of solar approach. So, if 3I Atlas were a normal comet, we'd expect signs of this. We'd expect asymmetrical jetting, a rotating or tumbling nucleus, sudden surges of brightness as volatile pockets explode, random shifts in trajectory due to outgassing forces, a visible coma expanding and contracting with solar input, possible fragmentation near gravitational encounters, but that's not what we're seeing. 3I Atlas has shown a level of stability that defies expectations. Its coma is controlled, its tail is narrow and well-defined. There is no indication of tumbling, no rapid changes in its brightness curve that would signal rotational instability. And perhaps most critically, its trajectory is too smooth. For a comet interacting with Jupiter's gravity, we should expect turbulence. The sheer mass of the gas giant, combined with the residual solar heat the object is still absorbing, should be pulling material off its surface. That kind of stress almost always leads to asymmetry, especially in the case of interstellar comets, which have no experience with this kind of environment. And yet, 3I Atlas behaves like it's insulated from chaos. There's no evidence of thermal fragmentation, no sign of a disintegrating core, no uncontrolled jet activity, just a tight, stable path, one that began curving before it entered Jupiter's zone of influence, and that raises a critical distinction. A comet responds to forces. It's passive. It brakes when heated, turns when pushed, and moves only where the laws of celestial mechanics allow. But 3I Atlas doesn't appear to be responding to Jupiter. It appears to be anticipating it, and that anticipation, the early curve, the stable axis, the smooth acceleration, introduces an uncomfortable thought. Because comets don't plan. They don't align for assists. They don't hold their shape under stress. And they don't execute velocity changes with the calm, deliberate timing we're now watching unfold. Which leaves us with two possibilities. Either this is the most stable, symmetrical, structurally sound interstellar comet ever observed, one that just happens to be executing a flawless approach vector near the largest planet in our system. Or it's something else, something with the ability to calculate, something that's not just surviving Jupiter's pull, but using it, and that is not what we'd expect from a comet. In orbital mechanics, there's a kind of beauty to precision, a subtle elegance in the way a calculated path curves through space without resistance, without chaos. And in the case of 3I Atlas, that beauty is becoming unsettling, because what we're now seeing is not the jagged, irregular arc of a crumbling object. It's the opposite. It's a textbook perfect inbound curve, one that resembles the navigational path of a probe, not the passive drift of a comet. The data doesn't lie. Observatories across the globe, including the Subaru telescope in Hawaii, the La Silla Observatory in Chile, and the Mount Lemmon Sky Center in Arizona, have all confirmed the same measurements. The approach angle of 3I Atlas is within half a degree of what mission planners would use for a gravitational assist around Jupiter. Not just close, precise. What does that mean? It means the object isn't just entering Jupiter's sphere of influence, it's threading it, sliding into the zone where gravity can be harnessed, not just felt, a region where a slight angle difference can mean the difference between acceleration and destruction. Space agencies like NASA and ESA use supercomputers to calculate this kind of entry vector for decades in advance. Thousands of simulations are run to ensure that a probe doesn't miss its assist window. The timing has to be perfect, the distance exact, the vector locked in before the object even arrives. That's what 3I Atlas is doing right now. But here's the part that's impossible to ignore. The curve didn't begin inside Jupiter's gravity well. It began before it, well before. As early as January 2nd, over 48 hours before any significant gravitational interaction, orbital projections began to show a deviation, not caused by outgassing, not caused by solar radiation pressure, just a clean shift in arc. Gradual, symmetrical, persistent. Natural comets don't do this. They drift, yes, they tumble, they fracture, and sometimes their paths change, but always as a response to external forces, never as an anticipation of them. But 3I Atlas, aligned. Its arc adjusted in a way that suggests the object had a goal, an exact entry angle into Jupiter's corridor of influence, an alignment that would allow it to convert a portion of Jupiter's orbital energy into outbound velocity, the very same method used by Voyager 1 to escape the solar system decades ago. That's not a natural drift. That's a navigational maneuver, and it gets stranger. The object's orientation, as measured by polarimetric imaging, remained fixed throughout the entire arc adjustment. This means that not only was the object changing direction, it was holding its rotation axis steady. That's not just difficult for a natural object, it's nearly impossible. Comets vent. They spin. They react to sunlight by developing rotational torque, but 3I Atlas stayed level, as if it were aware that a steady orientation was required to maintain trajectory. It behaved like a vehicle, and if that's true, if we're watching a slingshot maneuver, then this isn't just a moment of curiosity, it's a moment of revelation. Because such a maneuver requires forethought. It implies a navigational system. It implies a purpose. It implies this isn't just an object passing through our solar system, it's an object using it. And perhaps most provocative of all, this trajectory matches no known prior curve from any interstellar body. Not Oumuamua, not Borisov, not even the odd long-period comets we've watched dance near the outer planets. This is new. An inbound curve too clean, too precise, too perfect to be chance. And that may be the moment we stop calling it a comet and start calling it something else. Every object in space leaves a trail, not just in dust or gas, but in data. And over the last several days, that trail from 3I Atlas has become more puzzling, more electric and more controlled than ever before, because something has changed. As the object adjusted its trajectory toward Jupiter, ground-based observatories began to notice a subtle shift in brightness. But this wasn't the usual kind of shift you'd expect from a comet responding to solar heat. It wasn't chaotic, it wasn't sharp, it didn't rise and fall with sublimation events or flare-ups of outgassing. Instead, it was gradual, smooth, predictable. Astronomers tracking 3I Atlas from facilities in Arizona, Chile and Australia began logging an increase in luminosity, not in the coma, not in the tail but in the nucleus itself. And not just any increase, a spectral brightening in specific bands, particularly in the ultraviolet and near-infrared. This shouldn't be happening. At its current distance from the Sun, solar radiation is weaker. Most comets begin to fade as they move beyond perihelion. Their activity wanes, jets slow, reflectivity decreases as fresh volatiles retreat beneath the surface. The coma expands and thins out, but not this time. Instead, 3I Atlas began glowing more brightly, not explosively, not erratically, just steadily, like a system gathering charge, and it wasn't just visual. That same week, the Stereo A spacecraft registered a localized anomaly in the solar wind, a compression region that passed near Jupiter's orbital track. It was faint, it wasn't associated with a solar flare, but it aligned almost precisely with 3I Atlas's position. Inside that compression region was something unusual, a fluctuating electromagnetic signal. Weak, non-repeating, but real. A slight distortion in the normal background static of solar wind, like a pulse trying to hide beneath the noise. Was it just turbulence? Random interference? Maybe. But then came the particle data. The James Clerk Maxwell telescope, operating in the sub-millimeter band, logged an unexpected spike in hydroxyl emission. Not from widespread sublimation, but from a concentrated release near the core. The pattern suggested something directional, a controlled discharge of material rather than the usual chaotic venting, almost as if the object was letting off pressure or preparing for something. Some observers likened the behavior to that of a capacitor charging and then releasing, a slow build of energy followed by a sudden, localized drop, not explosive, but intentional. Even more intriguing was the spectral fingerprint. When astronomers ran analysis on the reflected light, they found something missing. The typical markers of dusty coma particles, silicates, hydrocarbons, frozen volatiles, were reduced. In their place, more consistent readings appeared. Reflectivity had increased. Polarization had shifted slightly. This led several research groups to propose a simple, but extraordinary idea. What if we're not looking at increased brightness from gas release, but from the surface itself? What if 3i Atlas is rotating a reflective structure toward the Sun, a mirror-like panel, a flat surface? A geometric feature designed to absorb or redirect solar energy with higher efficiency. That would explain the increase in ultraviolet reflectivity. It would explain the polarized light patterns. It would explain the steady rise in brightness without chaotic behavior. And perhaps more importantly, it would suggest intent. Because natural comets don't shift panels. They don't reveal mirrored structures. They don't respond to orbital positioning with spectral alignment. But probes might. And if 3i Atlas is building up energy, positioning itself to charge, to absorb, to reflect, then we're not just watching a cosmic rock fly by. We're watching a system, a mechanism, and maybe we're watching it prepare to fire, not a weapon, but a maneuver, the kind that requires power, the kind that needs light, the kind that happens right before a slingshot. Some events in space are dramatic, supernovae, collisions, flare eruptions, but others are subtle, quiet, barely detectable. Yet their implications echo louder than explosions. That's where we are now with 3i Atlas. Because as it approached Jupiter, something changed. Not loudly, not in a burst of activity, but in the most telling way imaginable. A shift in orientation. And not just any shift, a directional one. Astronomers watching the object's tail began to notice something strange. The angle, previously aligned consistently away from the Sun, began to deviate. Not wildly, not erratically, just slightly. A soft pivot by only a few degrees, enough to register on time-lapse imaging, enough to appear in comparison overlays. At first glance, this could be dismissed as a product of viewing geometry. The angle between the Sun, the object, and Earth constantly changes. That can make tails appear to move even if they don't. But this wasn't just a visual illusion. Spectral readings confirmed a slight reorientation of dust flow. The tail's apex, its point of origin at the nucleus, was shifting. The direction of outflow was no longer purely anti-solar. It had become lateral, not away from the Sun, not toward Jupiter, but offset. A directional deflection, like a steering vector, and it gets even stranger. This reorientation didn't occur during a sudden burst of gas release. There were no visible jets activating, no thermal surges, no flare events. Instead, the entire shift happened in a window of under 6 hours, without visible outgassing, without fragmentation, and without rotational instability, which means this wasn't caused by chaos. It looked like something had applied a tiny, precise force, and that leads to one of the most compelling and controversial possibilities of all, a silent thruster effect. On Earth, thrusters are loud, hot, and bright. But in the vacuum of space, propulsion can be almost invisible, especially if it's done using cold gas, a compressed inert gas like nitrogen or xenon released through a small nozzle to generate low but precise thrust. This is how satellites reorient themselves. It's how attitude control systems work on spacecraft. They don't blast themselves into new directions with roaring engines. They whisper their way into alignment. If 3i Atlas emitted a tiny jet of vaporized gas in just the right direction, at just the right time, it could alter its orientation without ever revealing it to the naked eye. That kind of precision would explain what we're seeing now. It would explain the slight tail deviation, the stable brightness curve during the maneuver, the lack of rotational wobble after orientation shift. In other words, it would explain how the object changed direction without losing control. But why would a natural object do this? Outgassing-induced thrust in comets is almost always accidental. It comes from uneven heating, fractured surfaces, or buried ice pockets suddenly exposed. The force is random. The rotation is unpredictable, and the results are usually violent, spins, wobbles, even breakups. But this wasn't random. This wasn't violent. This was controlled. Multiple observatories reported the same stability afterward. No spin increase, no coma disruption, no surge in gas emissions. The only thing that changed was the object's angle. That's the hallmark of a vehicle, not a rock. And if this was a thruster effect, even a primitive one, it changes everything. because it means 3i Atlas isn't just drifting into Jupiter's gravitational corridor, it's steering into it. No engine fire, no visible plume, just an invisible correction, like a probe adjusting its trajectory before a maneuver. And that raises the most unsettling possibility so far. If 3i Atlas has just made a course correction, then it's not finished. It has somewhere it still intends to go. Something changed as 3i Atlas glided into the outer edges of Jupiter's gravitational sphere. It wasn't just a passive approach anymore. Subtle shifts in its trajectory suggested interaction, not just being pulled, but somehow responding. For weeks, astronomers watched as the object's forward motion began to accelerate, and it didn't behave like a comet merely falling into gravity's grip. It began to angle itself, tilting, ever so slightly, as if adjusting for precision. Gravitational slingshots, also known as gravity assists, are a well-understood method used by spacecraft to gain speed without using additional fuel. A probe like Voyager or Juno can loop behind a planet like Jupiter, stealing a bit of its orbital energy and catapulting forward at dramatically increased speed. But what 3i Atlas was doing didn't follow the clean logic of planned trajectory. It was more erratic, but purposeful. Multiple observatories noted that the object's coma was not symmetrical. One side glowed hotter and brighter than the other, suggesting that gas and dust weren't being expelled in a uniform reaction to solar radiation. Instead, one side appeared active, the other calm. And strangely, the direction of activity didn't line up with its angle to the Sun. It seemed to respond to Jupiter's magnetosphere more than the solar wind. A slingshot maneuver requires an exact trajectory to work. If the object is too early or late, or if its angle is off by just a few degrees, the energy transfer fails. But 3i Atlas seemed to be threading a needle between chaos and calculation. Its velocity increased just before periapsis, its closest point to Jupiter, and the shape of its tail curved unnaturally. Some thought it might be breaking apart. Others thought it was firing jets. Jetting from a comet is a normal process. As frozen gases heat, they erupt through fissures and cracks, forcing material away and nudging the body in the opposite direction. But here's the mystery. The bursts from 3i Atlas came at times when the heating didn't match. Temperatures were stable, yet jets ignited. It was as if the object wasn't just reacting, but choosing, initiating thrust not by natural temperature rise, but by internal command. The theory sounds implausible until you realize the energy at stake. Jupiter's orbit holds immense angular momentum, and even a slight trajectory adjustment at this range could radically alter where 3i Atlas goes next. It could spiral into the Sun, it could swing towards Saturn, or more dangerously, it could aim back toward the inner solar system. Astronomers at Mauna Kea and La Silla ran parallel simulations. When they input the sudden angular adjustment and boost in velocity, the model produced something unexpected, an exit path perfectly aligned with Earth's orbital plane. Not immediately intersecting, but close enough to create a corridor of influence, what's sometimes called a gravitational funnel. This was no longer a random pass, it was a maneuver, and it was working. What's more, radar echoes from Jupiter's deep radio observatories picked up something strange, a thin echo line traced back to 3i Atlas, a delayed bounce, not consistent with its mass alone. It implied a trail, like a structure or dense material creating interference. Could it be a tether, a fragment, or something else entirely? Whatever it was, the object was no longer passive, it was gaining momentum in a controlled arc, its tail thickened, its leading edge glowed. And most importantly, its heading was locked, no longer drifting, but aiming, like a slingshot loaded and released with purpose. But what was it aiming for? The shift in momentum wasn't just mechanical. It suggested intelligence, or at the very least a non-random system of control. As Jupiter's magnetic field began to stretch and distort in response to the object's passage, one question echoed in every observatory. Was this a coincidence of nature, or the first act in a calculated journey? And if it was the latter, what came next would decide everything. As astronomers continued to refine their models, a subtle but undeniable angular deviation emerged in 3i Atlas's path. It wasn't sharp or sudden, it was gradual, like the soft turning of a ship in deep water. Over time, however, The angle of its trajectory relative to the solar plane began to diverge from earlier projections. Initially, this deviation was thought to be observational noise, minor errors caused by instrumentation drift, solar glare, or temporary fluctuations in signal processing. But once the data was corrected and cross-referenced across multiple observatories, a consensus began to take form. The angle had changed, not dramatically, not in a way that would set off alarms, but it had changed enough that it could no longer be dismissed. That was when the word slingshot stopped being a metaphor. It became a working hypothesis. The shift occurred just after 3I Atlas's closest approach to Jupiter's outer influence, still distant enough to avoid capture, but close enough to feel the full sweep of the gas giant's gravitational landscape. And the timing was too precise to ignore. The angle adjustment had begun during the peak window of influence, when Jupiter's tug would have been most effective. Some liken the motion to a cue ball grazing the edge of a table, not rebounding completely, but bending just enough to alter the entire outcome of its future path. The change was measured in arc seconds, barely perceptible without long-term comparison. But on a scale of interstellar distances, even those minute adjustments can mean the difference between outbound silence and a redirected return. Speculation spread through the scientific community. If the change was purely natural, a product of orbital mechanics, it would still be a remarkable event, one of the cleanest demonstrations of a naturally occurring gravitational assist in recent observation history. But if the alteration was intentional, if 3I Atlas had responded in some way to Jupiter's field, then it was no longer just a passive object. It was navigating. The angular shift wasn't just lateral. It also carried a small but measurable dip in inclination, a movement slightly downward, closer to the ecliptic. That detail set off another wave of quiet theorizing, because it implied not just a change in direction, but a possible correction, a course refinement, as if something on or within the object had sensed the need to lower the trajectory to remain in the orbital sweet spot for its next phase. That dip aligned it closer with Earth's plane of rotation. This was not definitive proof of intent, of course, but it set in motion a cascade of recalculations. Supercomputers at JPL and ESA were reloaded with updated parameters. Observatories recalibrated their predictions, and in every model, one word began to reappear with increasing frequency: encounter. Because if 3I Atlas had used Jupiter as a slingshot, then the Earth, sitting neatly in the path of that new vector, may not have been a coincidence. It might have been the destination. What disturbed many wasn't the idea that a space rock had changed direction. That happens. Comets, asteroids, even rogue objects can experience gravitational interactions that subtly alter their path. What unsettled people was the apparent precision, the elegance, the timing, the way every turn, dip and curve seemed to map to a clear orbital advantage. By the end of that week, a new category was quietly added to several observatory tracking systems. Not hazard, not alien, just a placeholder tag, unknown guidance event. And for those watching closely, it marked the beginning of a new kind of question, not about how fast or how far the object was moving, but why it seemed to be choosing its own path at all. As 3I Atlas continued along its newly shifted trajectory, something even stranger began to unfold, this time not in its path, but in the space surrounding it. Multiple observatories, including those equipped with wide-spectrum interferometers and magnetoplasma detectors, began reporting subtle fluctuations in the field immediately surrounding the object. It wasn't ionization, it wasn't a debris trail, it wasn't even the usual electromagnetic hum we expect from fast-moving objects interacting with the solar wind. Instead, it was something eerily uniform, an energy dispersion field. The term was proposed hesitantly at first. It carried implications. To describe the space around 3I Atlas as a field meant admitting there was structure to it, or at the very least some consistency that couldn't be explained by randomness. And the pattern that emerged from this consistency was fascinating, because it appeared as a soft interference band, spreading out in symmetrical rings, extending far beyond the core of the object. In some measurements, this dispersal zone reached thousands of kilometers wide. At first, this was attributed to wake turbulence, perhaps solar radiation interacting with volatile gases being released from 3I Atlas as it crossed warmer thresholds in space. but there were no gas emissions, no outgassing, no trail. In fact, 3I Atlas remained one of the cleanest objects ever tracked. No coma, no tail, just the object, dark, fast, angular, and now a structured field behind and around it. The dispersion was not chaotic. It did not resemble radiation decay or solar echo. It pulsed, slowly, rhythmically, like the soft ripple of a signal echoing through an unseen medium, a pattern that repeated every 38 minutes. This periodicity was consistent across multiple instruments. Whether measured in electromagnetic flux, gravitational microvariations, or thermal infrared distortions, the signature was undeniable. Something was interacting with space-time in a patterned, intelligent-seeming way. It was not loud, not aggressive, but precise. Scientists began cross-referencing this pattern with known natural sources: pulsars, magnetars, variable stars, black hole accretion waves. Nothing matched. One researcher from the Max Planck Institute made a bold comparison. She noted that the periodic dispersion bore eerie similarities to phased array transmission patterns used in deep space communication, where controlled directional pulses allow for long-range signal focus without broadcasting omnidirectionally. In other words, 3I Atlas's field might not be a byproduct of motion, it might be a transmission. This ignited a whisper war between observatories. Publicly, institutions released vague, cautious language: anomalous energy modulation, ambient dispersion variance, non-thermal field irregularities. But internally, teams were mobilized. Data sets were encrypted. Peer sharing was halted. The term technosignature was floated in several classified email threads. No one wanted to say it outright, but the implication was becoming harder to avoid. What made this more chilling was the fact that the energy field had not been there prior to the Jupiter encounter. In earlier frames, when 3I Atlas was still outbound and uninfluenced, the surrounding vacuum had been clean. No pattern, no pulses, no dispersion cloud. But in the weeks after the angular shift, the field appeared, as if activated. Was it a wake? A shield? A beacon? And why now? The silence from official agencies became telling. NASA, typically vocal with public findings, offered no official briefings on the energy field. ESA quietly removed live feed references to Atlas tracking. China, whose fast scan arrays had been early in confirming the shift, went silent altogether. The only thing that continued to circulate were leaked graphs, blurry spectrograms showing the rhythmic waveforms emanating from the object, overlaid against deep space telemetry maps. These maps showed how far the pulses had travelled, and by week's end, one terrifying truth emerged. The outermost ring had already passed Earth's orbit. We didn't feel it, we didn't see it, but the pulse had already crossed us. Whatever it was, signal, scan, field distortion, Earth had already been touched by it, and no one could explain what it meant. As 3I Atlas continued its path around Jupiter, observers on Earth began noticing something that quietly defied expectations. Every model predicted a certain amount of acceleration, a precise arc, a predictable path based on gravity alone, but what they were seeing didn't quite line up. The object wasn't just speeding up, it was doing so in a way that suggested momentum was being added with near-perfect timing, almost deliberately. This is where things started to take a strange turn in observatories across the globe. In a standard gravitational slingshot, a comet approaches a planet like a speeding bullet, skimming just close enough to gain a burst of energy from the planet's own motion and gravity. This isn't science fiction. It's how we've flung spacecraft across the solar system for decades. But with 3I Atlas, something about the acceleration profile was too clean, too efficient. Instead of the expected wobble, the small shifts, the chaotic dance of an icy rock being pulled by multiple forces, what scientists saw looked like controlled precision. The shape of the tail was the first clue. As the object reached its closest pass near Jupiter, its tail didn't whip or distort the way most icy bodies do. It flattened, straightened, narrowed, and instead of flaring up in response to solar wind or magnetic distortion, it pulsed, almost like it was channeling force through a narrow funnel. That's when some analysts began quietly suggesting something radical. 3I. Atlas might not just be passing through the system, it might be managing its motion within it. It wasn't just a simple acceleration, it was a refinement, almost like a ship adjusting its sails during a storm, tacking precisely to maximize speed and control. This led to a difficult question. If it was managing momentum, how? Jupiter's immense magnetosphere stretches tens of millions of kilometers, larger than the Sun itself. Within this vast magnetic field, currents flow in ways we still barely understand. Any object passing through could experience dynamic pressure, turbulence, and massive shifts in direction. For most comets, this causes chaos. Tails splinter, spin increases, sometimes even breakups. But 3I Atlas remained solid, stable, and focused. What puzzled researchers the most was what came after the slingshot. The object didn't just move away faster, it rotated slightly, subtly, yet unmistakably. The rotation aligned it with a new direction that had not been part of its original trajectory. It was no longer just moving away from Jupiter, it was adjusting, curving, plotting a new path. It was here that the term momentum shaping began surfacing in internal documents. Not propulsion, not thrust, but a kind of adaptive manipulation of external forces, using magnetic pressure, solar wind, gravitational pull, all woven into a trajectory that resembled an engineered maneuver. If this theory were correct, it wouldn't just change our understanding of 3I Atlas, it would redefine what kinds of motion we expect from objects labelled as comets. Because no known natural body shows this kind of consistent directional shaping across so many environments. The observers weren't jumping to conclusions, they were watching, waiting, cross-checking with other gravitational interactions, Saturn, Mars, even smaller moons like Ganymede, to see if the object would repeat the behaviour elsewhere. If momentum shaping was real, there would be signs, a pattern, a rhythm, and in the next chapter that pattern would become impossible to ignore, because what 3I Atlas did next wasn't just directional, it was intentional. At first, it looked like a simple turn, a smooth gliding adjustment, nothing too abrupt, nothing chaotic. But as the data poured in from multiple telescopes, the collective realization dawned. 3I Atlas wasn't just coasting on momentum, it had made a decision. In the world of astrophysics, motion is everything. The speed of light, orbital vectors, inclination angles, all these define the dance of celestial objects. And most of that dance is predictable. Even chaos has patterns. But what 3I Atlas displayed after slingshotting around Jupiter wasn't predictable. It was calculated. It began with a pivot. Using gravitational influence as if it were a rudder, 3I Atlas curved, not outward toward the distant stars, but inward, slightly, minutely, subtly enough that older telescopes might have missed it. But modern instruments, especially those working in tandem with Lagrange point satellites and radio tracking stations, picked up the shift. The arc was changing, not randomly, not under duress, but with a precision that looked disturbingly like a chosen vector. That pivot aligned it closer to Earth's orbital plane, not directly toward our planet, but no longer flying at the angle it once had. It was now entering a corridor that passed through the inner solar system, threading the gravitational influences of Mars, Earth, and Venus in a sequence that looked eerily like navigation. For a natural object, that would be statistically improbable. Comets don't plot paths. They tumble, they drift, they react, they don't choose. But this movement, it looked like a choice. Researchers at ESA's Near-Earth Object Coordination Center were the first to label it what it might be. An intent trajectory. A path not dictated by passive physics, but one that uses physics with intent. Think of it like a ship using ocean currents, not just floating on them. It doesn't mean the ship is powered, it just means someone's at the helm. The shape of the object's antitail shifted again. For days it remained rigid, pointing straight back from its direction of travel. Then slowly it bent, not flared, not twisted in the wind, but arced toward the sun. This kind of behavior doesn't show up in textbooks. A bending antitail implies influence, either from internal jets or from a structure capable of redirecting material flow. And it did this without shedding mass. No debris fields, no signs of stress, just adaptation. Planetary defense teams, once passively monitoring, began running new simulations. If this object was aligning toward inner system targets, even if accidentally, it required priority tracking. But with every new data point, the accident theory became harder to defend. Meanwhile, solar observatories picked up something even more stunning. 3i Atlas was beginning to sync with the sun's magnetic field lines. Not resist them, not get distorted by them, follow them. This phenomenon, magnetic harmonics, has only been theorized in high-level physics. The idea that an object could ride the sun's magnetosphere like rails, using it as a sort of directional guide through space, had never been observed, until now. The implications of magnetic field surfing were massive, not just for understanding 3i Atlas, but for questioning whether we were looking at a natural comet at all. If it could read and align with magnetic fields, it was doing something we've never seen in an unpiloted body. In a quiet observatory in South America, one scientist wrote it in their notes first. It's not where it's going, it's how it's choosing to get there. And the next step on that path would be even harder to explain, because it didn't just pass through space, it reacted to what was already there. For days, space agencies assumed the trajectory shift was the most unusual thing 3i Atlas would do. But that assumption didn't last long, because after the pivot something stranger happened, something that made researchers rethink everything they thought they knew about how a comet or any interstellar object should behave. It began with a subtle deflection. Not a gravitational slingshot this time, not course correction based on any known external force. Instead, it looked as though 3i Atlas was responding, not just navigating, but reacting to objects, fields, and phenomena it encountered. As it neared a region thick with solar plasma turbulence, charged particles and magnetic distortions that radiate from older solar events, 3i Atlas adjusted its position. Not slightly, not randomly. It moved around the turbulence. Solar probe data showed a dense patch of chaotic high-energy plasma, one that would be difficult for any unshielded object to pass through cleanly. The plasma's effects weren't deadly, but they could have disrupted the delicate tail structures we'd been observing. But rather than plunging straight through the storm like a rock on a path, 3i Atlas veered. That shift in motion wasn't a drift. It had all the hallmarks of avoidance. The comet bent its path slightly up, then back down, rejoining its previous vector after it had cleared the disturbance. In orbital dynamics, such maneuvers aren't impossible, but this one had timing, it had grace, and it had intention written all over it. NASA and ESA simultaneously logged the movement and reran all simulations. None of the previous orbital predictions had accounted for such maneuvers, because nothing natural does this. Then came the most shocking part. Several days later, as it continued through the inner system's approach corridor, 3i Atlas entered a zone riddled with meteoroid debris, leftovers from earlier collisions, space junk fragments, and minor asteroids that never coalesced into anything significant. To scientists, this was a standard part of the interplanetary environment, occasionally dense, but navigable. It was assumed that 3i Atlas would pass through without much incident, but then it paused. More accurately, its speed reduced, slightly but measurably. A reduction in acceleration from an object with no engine, no onboard propulsion, no radiation burst, no sublimation of materials. It didn't slow due to resistance, it simply decreased speed as it approached the denser debris field, and as the main body passed through the zone, it began rotating. This rotation wasn't random, not a tumbling spin. It was slow, controlled, oriented. Its axis aligned with several approaching obstacles, and as it moved, the tail, both normal and anti-tail, seemed to shift shape, almost like rudders. And once again, 3i Atlas emerged from the field without a single visible impact. Dozens of fragments were travelling fast enough to graze or strike any body passing through. The probabilities favoured at least minor collisions, but when scientists compared before and after high-resolution images taken by orbiting probes, nothing had changed. Not the shape, not the albedo, not the tail distribution. 3i Atlas had passed through a minefield, unharmed, untouched. A few dared to speak the word out loud: evasion. Could this object, comet or not, be analysing the space around it? Could it be interpreting fields and masses and making real-time adjustments? One physicist on the Parker Solar Probe team suggested a concept that hadn't been used in decades: reactive navigation. This wasn't the same as path prediction or automated course plotting. Reactive navigation meant the ability to detect immediate threats and respond, organically, smoothly, intelligently. In spacecraft engineering, this kind of autonomy is reserved for experimental AIs and theoretical quantum-based sensors. So the question wasn't just, how did it avoid the field? It was now, unavoidably, what kind of system is embedded inside 3i Atlas that makes this possible? Because only two explanations were left on the table. Either nature had evolved something we had never seen, or this was not a product of nature at all. There was a moment when the instrument stopped recording new changes. For a full 30 minutes, all of Earth's telescopes tracking 3i Atlas reported a strange stillness. It wasn't that the object had vanished, quite the opposite. It was still there, centered in their viewfinders, but something had changed. It was as if the object had momentarily stopped evolving, halted its color shifts, paused its spin, and entered a kind of suspended animation. The team at the South African Large Telescope first reported it. Others followed. But the real revelation came when scientists overlaid that time frame with Jupiter's powerful magnetic environment. The object had entered the edges of Jupiter's massive radiation belts. These belts, more powerful and extensive than Earth's Van Allen belts, are composed of charged particles swirling chaotically in powerful loops. Any spacecraft passing through them would suffer intense radiation bombardment. But 3i Atlas wasn't reacting like a fragile probe. It wasn't breaking down or heating up. It was still, as though listening. Observatories studying the area at different wavelengths noticed another anomaly. Radio silence. Background cosmic noise, usually constant in that part of the sky, was dampened. As if the object, Jupiter, or something between them was absorbing or blocking signals. The quiet wasn't just physical. It was electromagnetic. The question arose, what kind of material would allow 3i Atlas to move through this hazardous region without reaction? Some postulated it could have a kind of naturally self-regulating electromagnetic shield, not unlike the way certain spacecraft are designed to dissipate charge buildup. But nature rarely builds such precision on accident. The shape, the composition, the pores, it all pointed to intentionality, or at least a kind of evolutionary path we don't yet understand. A comet or asteroid that can hold formation, maintain heat consistency and remain unaffected by Jupiter's radiation storm is already a statistical outlier. But to pause inside that storm, that changed the tone of the entire investigation. Others suggested an entirely different approach. Perhaps the pause wasn't 3i Atlas waiting, but recalibrating. Jupiter's radiation belts are not evenly distributed. There are pockets of more intense plasma, places where magnetic reconnections occur in bursts. If 3i Atlas was adjusting its tail, its spin, or its orientation to prepare for these zones, it would suggest a kind of spatial awareness. The theories piled up, some grounded in plasma physics, others in speculative astronomy. But none could explain why this pause happened in such a specific window, and none could explain what happened next. As the object moved past the belts and into a clearer region of Jupiter's magnetosphere, its tail flickered. Not in a random burst, but in a wave, like a whip being cracked. Multiple observatories recorded the moment. It was as if 3i Atlas had reawakened. New materials began venting, the anti-tail shifted direction again, and the object brightened slightly in visible spectrum. The momentary silence was broken, and the motion resumed. Yet the mystery deepened. Why would an interstellar object use Jupiter's radiation belts as a waypoint? Some began to see the movement not as a slingshot maneuver in isolation, but as a process of interaction. Perhaps the object was not just using Jupiter for trajectory, but harvesting something. Energy, data, or even acceleration from interactions beyond our understanding. The radiation pause, once considered a quirk, became a central focus, and for the scientists watching on Earth, it was clear. 3i Atlas wasn't just flying by. It was reacting, responding, and engaging with its environment in ways no known comet ever has. After the eerie pause within Jupiter's radiation belts, as 3i Atlas resumed its motion, something unprecedented happened. Earth-based radio telescopes began receiving a strange burst of data-like pulses. It wasn't a normal signal. It wasn't a single frequency or a clean tone. It was a scrambled set of pulses that repeated every 1.8 seconds, spread across a narrow-band frequency, not usually associated with natural cosmic emissions. At first, teams dismissed it as interference, but when the same pulse pattern was picked up by observatories in Chile, Japan, Australia, and Hawaii, all separated by time zones and magnetic latitudes, scientists were forced to reevaluate. The most baffling part wasn't just that it appeared everywhere at once. It was the fact that the signal only began after the moment 3I Atlas exited Jupiter's radiation belts. The timing was precise, too precise to ignore. The burst came in short streams, paused for 4 seconds, and then started again, as if transmitting in structured intervals. It was unlike any known comet interaction, unlike solar wind collisions, unlike magnetic reconnection echoes. These pulses had rhythm. They had order. Physicists working in deep space communications started analyzing the burst pattern. Using Fourier analysis and machine learning signal detection algorithms, they discovered the pulses weren't uniform. Some were phase-shifted. Others were split into high and low-energy echoes. It resembled something between a ping and a handshake, a two-part sequence, as if one signal were being sent and another mirrored back. But mirrored from what? That question sparked a debate that would divide institutions. One camp believed it could be 3I Atlas itself emitting these pulses, perhaps releasing stored electromagnetic energy after its exposure to Jupiter's belts. They theorized that the object might have absorbed particles or interacted with the belt's intense magnetism, converting that into directed energy release, similar to how lightning triggers electromagnetic echoes on Earth. The other camp believed the signal was being reflected, that something else was behind or near the object, something not yet visible on our instruments. They argued that if 3I Atlas were natural, any emissions from it would be random, chaotic, and broadband. But this was narrow, tight, repetitive, and the spacing wasn't arbitrary. It fell into ratios eerily close to the Golden ratio and Fibonacci sequences when mapped across harmonic intervals, a pattern often found in biological systems, not rocks or ice. One group in Canada ran a simulation assuming the signal was a result of resonant interaction, a kind of ping triggered by the objects passing through high-energy magnetic lines. The model showed that a rotating structure, if made of conductive material and equipped with simple, resonating cavities, could potentially produce this kind of signal naturally, if you define naturally as something that evolved or was designed to use it. In a late-night live stream that broke 10 million views in 24 hours, a Harvard astrophysicist went further. He proposed that the pulses weren't just data, they were a test, a kind of universal echolocation. He claimed that if 3I Atlas was not alone, and if something was shadowing it or guiding it, these pulses were a way of clearing the air, measuring the space ahead, mapping radiation fields, detecting density shifts, or even triggering dormant satellites or relays embedded in interplanetary space. Then something even stranger happened. On the final echo burst of the signal, just as Earth's instruments captured the last wave, a single beam of light, concentrated, column-like, and ultraviolet heavy, was seen extending from the object toward Jupiter's upper atmosphere. It lasted only 2.4 seconds and was captured by Juno's imaging equipment. Not a natural tail, not a flare, but something narrow, controlled, and precise. Suddenly the idea of a data pulse wasn't speculative anymore. It was happening, real time, recorded, triangulated. And for the first time since the object entered our solar system, humanity realized it might be listening, or worse, communicating. As 3I Atlas carved its way across the darkness near Jupiter, a shift began to appear. At first it was nearly imperceptible, a minor deviation in its projected path, not enough to alarm mission controllers, but just enough to raise a few eyebrows. Over the next 12 hours, this deviation began to build. Scientists didn't call it a correction. They didn't label it a mistake in trajectory prediction. What they observed was something far more curious. The object's velocity was increasing, and not randomly. It was directional. Normally, objects accelerating in the outer solar system require a cause. Solar radiation pressure isn't strong enough this far out. Outgassing could offer a temporary push, but Atlas wasn't behaving like a typical comet. Its tail was not flaring, and no jets were observed, and yet the object wasn't just speeding up. It was doing so with surgical consistency, as if it knew where it was going, as if something invisible had taken control of its path. Telescopic arrays across Earth and orbit watched as the drift translated into a clean, smooth curve, not the kind of motion you'd expect from chaotic gravitational scattering, but the kind that suggested a deliberate realignment. The fact that this was occurring near Jupiter, a planet known for turning comets into wreckage, only made the behavior more striking. There was no fragmentation, no disintegration, no signs of tumbling or violent rotational change. Instead, The change in speed was linear, continuous, and stunningly precise. It was as if 3-Eye Atlas had found an invisible track in space and decided to follow it. For some, it echoed the classic hallmarks of a gravity slingshot maneuver, the kind used by spacecraft designed to use planetary mass as a catapult. But comets don't do slingshots with precision. They either swing wildly around the planet or break apart trying, and that's what haunted analysts most. The math worked. The maneuver, if it was one, followed the exact curve a human-engineered probe would take if it had programmed Jupiter into its slingshot calculations. There were no hiccups, no unexpected oscillations in the curve. It bent perfectly. That single fact forced a quiet shift in tone at many observatories. What was once called a natural object was now being discussed, not in press releases, but in private group calls and hushed back-channel emails, as something else, not necessarily artificial, but intentional, as if the physics alone wasn't enough to explain what they were watching. One possible explanation was buried in the gravity model itself. Jupiter's mass is so immense that even a minor pass within millions of kilometers can curve the path of a nearby object. But 3-Eye Atlas wasn't just being pulled, it was adjusting, steering, aligning itself perfectly with the outbound curve, and in doing so it changed not just its direction, but its mission. Its new course was sharper than expected, arcing with a kind of commitment that made its next trajectory clear. It wasn't going wide, it wasn't heading back into the Kuiper belt, it was narrowing toward the inner system. For the first time since its arrival, the question stopped being, where did it come from, and became, where is it going now, because the slingshot wasn't over. The real show, it seemed, was just beginning. As the slingshot completed, what followed sent shockwaves through every observatory, tuned into the live orbital feed. 3-Eye Atlas was no longer drifting, it was locked, and the vector it now followed cut straight across the orbital plane, narrowing toward the one place no one wanted to see it head. Earth. This was no longer a theoretical probability buried in simulations. This was now a projected certainty, a clean arc calculated by JPL, ESA, and independent physicists across the globe. It didn't mean collision. It didn't even guarantee a flyby. But what it did guarantee was proximity, close proximity. The kind that had once seemed mathematically implausible, yet here it was, right in front of them. At first, the raw numbers didn't feel real. Millions of kilometers in change, compressed down into a new trajectory that sliced across the inner system's plane like a cosmic scalpel. The math didn't just project a near-Earth approach, it narrowed it to a specific corridor, and the same corridor that was used for satellite launches. The same orbital window that most of our planetary observation satellites pass through. And it would pass through it in just days. The silence inside mission control rooms, in Pasadena, in Darmstadt, in Tsukuba, was deafening. No one spoke. They didn't need to. The new path was being plotted on wall-sized screens in real time, and the numbers didn't lie. 3-Eye Atlas was heading for a point just ahead of Earth's orbit, and Earth was moving toward it. Some still held out hope that this was just the tail end of a curved flyby, that once it passed the inner system, it would veer off again and head back out to deep space. But the curvature wasn't fading, it was sharpening. The new path resembled something closer to a rendezvous than a pass. What made this more unsettling was the velocity shift. Atlas wasn't just accelerating, it was adapting. Minor fluctuations in its course showed it was subtly adjusting to planetary gravity wells before they even had full effect. That kind of anticipation made no sense unless the object had either been here before or could compute gravity in advance, and comets, even the most mysterious, weren't known for that level of predictive correction. The real-time simulations began to sync up, and with each update, confidence in the trajectory grew stronger. Not wilder, not chaotic, just focused. And for the first time, the word targeting started to slip into conversations. It wasn't used in the official reports, it wasn't quoted in the media, but it appeared in Slack channels, private emails, encrypted Zoom calls between astrophysicists and government consultants. A few even checked to see if it had passed through any known Lagrange points, gravitational balance zones that might explain the shift. But it hadn't. It was aiming on its own. And if that wasn't strange enough, the timing made it even worse. Its new trajectory would bring it within observational range of every major Earth-based telescope in less than 96 hours. which meant there was no hiding from it. Whatever this object was, it had just put Earth in its line of sight. Nobody wanted to say it out loud, but the questions were now too large to ignore. Was this simply a gravity-assisted redirection, a natural slingshot gone strange, or was this object choosing Earth? Because if it was, we had less than 4 days to prepare, not for impact, but for encounter. And those who had dismissed the idea of an interstellar visitor returning with intent no longer had that luxury. By the time 3i Atlas crossed the 0.4 AU mark, something unprecedented happened. Every single observatory, from the dusty mountaintops of Chile to the wind-blasted highlands of Hawaii, from orbiting platforms to backyard telescopes operated by amateur astronomers, locked their instruments onto a single moving target. Not because they were told to, not because they were part of some coordinated international directive, but because they had to. The new trajectory wasn't just suspicious, it was mesmerizing. And for those watching from Earth, something about the angle, the brightness, and the eerie predictability of its movement began to feel less like celestial randomness and more like intention. That word, intention, shouldn't apply to comets. Yet the scientists found themselves whispering it in observatory halls and research labs. It was as if the object wanted to be seen, as if it had waited for the precise moment when Earth would be optimally positioned, not to strike, but to witness. And now that the moment had arrived, it was putting on a show no telescope could look away from. Hubble was the first to issue an updated deep-field image. What it saw was staggering. The outer structure of 3i Atlas wasn't just fragmenting or shedding gas like a typical interstellar comet. It was reorganizing. Within the structure of the tail, glints of internal geometry began to emerge, curved streaks of light forming symmetrical arcs. These weren't natural spirals, they looked manufactured. The James Webb Space Telescope followed suit, firing its infrared sensors directly at the heart of the object. The readings returned something that confused even the most seasoned NASA engineers. Layers. Not just heat layers or gas dispersion layers, but tiered shell-like formations, concentric and nested, like armor. Radio telescopes began listening again. They had tried before with no results, but now some began picking up faint modulations near the 1420 Hz line, the hydrogen line. The same frequency Carl Sagan once proposed would be the logical place to search for extraterrestrial signals. Was it real? Was it noise? Or was 3i Atlas simply reflecting our own broadcasts back at us? Even more disturbing, the timing. Every time Earth's rotation aligned a specific cluster of telescopes in Chile, the signal intensified for precisely 17 minutes, then vanished. A pattern. European Southern Observatory flagged it. So did Japan's Subaru telescope. So did a Canadian weather satellite that wasn't even designed to scan for this sort of thing. The correlation was undeniable. The object wasn't just visible, it was interacting. For the first time since the discovery of Oumuamua, institutions began holding classified briefings again. Not for fear of panic, but because no one wanted to jump to conclusions that couldn't be walked back. They needed confirmation, so they reached for everything. LIGO was contacted to see if any gravitational anomalies coincided with Atlas's new path. NOAA reviewed magnetospheric data to check for geomagnetic resonance. The US Space Force, which had mostly remained in the background, suddenly released a brief and deeply sanitized statement. Orbital objects are being monitored, but no one needed confirmation from defense agencies anymore. The world had eyes, and those eyes were seeing something no one could explain. 3i Atlas was now being tracked in real time by over 80 ground-based systems: infrared, ultraviolet, spectrometry, radar. It had become the most observed object in the history of astronomy, surpassing even Halley's Comet or the Moon during eclipse cycles, and yet, for all the scrutiny, it only grew stranger. The closer it came, the more impossible its structure looked, not because it was hostile, not because it was decaying, but because it didn't behave like an object shaped by chaos or chance. It looked composed, designed, and Earth was now the front-row audience. What we were witnessing wasn't just a trajectory shift, it was a cosmic performance, and whether it ended in revelation or catastrophe, we were all watching. Just as astronomers began to feel they had a handle on the trajectory of 3i Atlas, a new twist emerged. and it came in the form of an echo. While monitoring the tail structures of the object on January 4th, deep space antennae in Australia and South America reported something strange, a reflected signal. Not a standard emission and not a natural cosmic burst, but a bounce, a return pulse from a transmission that had been directed at 3i Atlas hours earlier. Signal bouncing isn't unusual in and of itself. Scientists have used radio waves to study the Moon, Mars, and even asteroids. You send a pulse out. If there's a surface solid or structured enough, it reflects back. But in this case, the signal that returned from 3i Atlas had shifted properties. It didn't just bounce off a rocky surface. It appeared to have modulated, changed, during its return. Something had interfered. What that meant became the subject of heated discussion. Some argued it was simple ionization. Maybe the tail of 3i Atlas had grown charged from its interaction with Jupiter's magnetosphere. Others suggested a denser core was responsible, a nucleus more complex than previously expected. But the third camp leaned into the gravitational slingshot theory. And for them, this signal change was everything. If 3i Atlas were using Jupiter's gravitational influence not just for propulsion but for positioning, steering its path, then some form of internal orientation would be required, whether by natural feedback loops, magnetically sensitive structures, or something even stranger. The object would need awareness, not sentience, but structure, design. This bounce suggested the presence of a dense reflective interior, not random dust, not broken up rock, but something capable of modifying a frequency. That's not something most comets can do. And the strange part was where the reflection came from. Not the outer tail, not the leading edge, but from the centre mass of 3i Atlas. A near-perfect echo from a region that should be chaotic and mixed. And what really caught the attention of astrophysicists was the shape of the signal's decay. It didn't just fade out randomly. It held form for a moment, like a pulse slowed in a medium, the way it would if it passed through liquid or through a dense honeycomb of material that momentarily absorbed, then re-released it. That opened up all kinds of new theories. Had Jupiter's immense gravity compressed 3i Atlas into a denser state? Was it a naturally layered object with strange inner stratification? A kind of onion shell model with hidden reflective layers? Or was this something else entirely, a relic from outside the solar system with a core unlike anything we've seen? The bounce wasn't just a fluke. Multiple tracking stations confirmed it, and while the signal strength was faint, the implications were not. For the first time, we had indirect evidence that something inside 3i Atlas was behaving like a structure. Not a snowball, not a cloud, something that could take in energy, hold it, and reflect it in a controlled way. It wasn't a transmission, it wasn't sending a message, but it was revealing its geometry. And that geometry now became the new obsession of observatories around the globe, because if 3i Atlas was about to slingshot around Jupiter, as the models predicted, then whatever was hiding at its core was about to get even closer and clearer. The race was now on, before the window closed, before it passed, because this bounce changed everything. As global attention turned to the mysterious signal echo, the visual data from January 4th's Hubble captures added an entirely new layer to the mystery. Scientists had been tracking the evolving tail of 3i Atlas, its length, composition, and angle. But something in the structure of the tail itself began to raise eyebrows. For weeks, the tail had been turbulent but relatively symmetrical, flowing outward in response to the solar wind and gravitational forces. But now, enhanced imaging revealed something patterned, not symmetrical, but intentional. Embedded within the outer layers of the tail, an angular formation had begun to appear. Not a line, not a curl, but a repeating arc, almost like an orbital track, curved, consistent, faintly glowing. It wasn't a cometary jet. Those shoot straight out from pressure beneath the crust. This was different. It stretched along the antitail spine like a filament. Long looping strands that bent inward, toward the object itself, as if spiraling in from the tail to the nucleus. At first, many thought it was an illusion, an artifact of image stacking or overexposure. But frame after frame, telescope after telescope, the same structure persisted. It moved with the comet. It warped slightly based on solar wind direction, but it never broke apart. It was stable. And it wasn't just visible in light. infrared sensors began to pick it up as well, registering a faint but real temperature differential along the arcs. They weren't just light shows, they were something. What were they? Some theorized magnetic filaments, like those seen during solar events, only on a vastly smaller, more focused scale. Others posited crystalline ejector or frozen gas chains, but those would fragment under this kind of velocity and exposure. These didn't. And that's when someone asked a question that hadn't been voiced out loud yet. What if these weren't natural structures at all? What if the tail itself wasn't just a byproduct, but part of the design? Because if 3i Atlas was rotating, and all evidence now pointed to a slow, deliberate spin, then these structures could be functioning like vanes. Directional stabilizers, components that use the outward push of ionized gas to subtly shift orientation, not steering in the traditional sense, but controlling posture, a rudder, powered by sunlight and plasma. And that's when another idea emerged. What if this wasn't the tail being manipulated by the core, but the core being hidden by the tail? The curvature of the filaments matched no known natural tail formations, but they did resemble something else: containment spirals, devices used in particle accelerators, or the magnetic bottles in nuclear fusion experiments. Loops designed not to radiate, but to hold. Were we seeing a comet tail, or a kind of exhaust vent? It was a disturbing thought, but a mesmerizing one, because if 3i Atlas had a core, dense, symmetrical, and capable of reflecting signals, and now we were seeing these heat-stable, geometrically spaced spiral arcs emerging in its tail, then perhaps we weren't watching a natural process unfold. We were watching a reveal, a slow, staged unmasking, like a veil being drawn back, like a machine powering up as it approached its next phase. And if that phase had anything to do with Jupiter, with its gravity, its magnetism, or its orbit, then the spirals might not just be stabilizers, they might be receivers, or emitters, or channels for energy storage. Suddenly every assumption about comets, tails, and space debris felt inadequate, because the structure wasn't random, and the timing wasn't accidental. 3i Atlas wasn't just interacting with our solar system, it was aligning with it. The moment scientists plotted the trajectory of 3i Atlas after its Earth flyby, all eyes locked onto one thing: Jupiter. At first, it seemed like a coincidence. The comet's altered path just happened to point in the direction of the gas giant. But January 4th's refined trajectory data changed everything. It wasn't just heading toward Jupiter, it was vectoring with precision. A straight-line approach might have been explainable. Gravity is, after all, a cosmic magnet. But this wasn't a straight line. It was a curve, subtle, controlled, and evolving with each passing hour. And it wasn't obeying the typical laws of orbital capture. This wasn't the chaotic slingshot path of a comet getting flung around the system. This was more like docking protocol. Jupiter's gravitational influence extends millions of kilometers into space, and any object that ventures near is inevitably pulled in, slung out, or swallowed. But 3i Atlas wasn't speeding up, it was slowing down. Telemetry indicated that between December 30 and January 4th, the object had reduced its acceleration by nearly 9%. Not because of drag, not because of any known force, but through an unknown mechanism, perhaps internal, perhaps electromagnetic. It was almost as if the object was matching velocities, preparing to enter a specific corridor, aligning itself with something beyond gravity. Scientists began looking at Jupiter's moons, Europa, Ganymede, Callisto, each one rich with water ice, subsurface oceans, magnetic anomalies. Were they the target? Was 3i Atlas aiming for a landing, or even a rendezvous? But the curve of the trajectory didn't aim for any moon. It pointed slightly above Jupiter's equator, toward its powerful magnetosphere, one of the strongest magnetic fields in the solar system, strong enough to trap radiation, strong enough to generate auroras that dwarf Earth's, and strong enough to interact with charged structures. That's when speculation reached a boiling point. What if 3i Atlas wasn't just passing by Jupiter, but needed it, for power, for data, for activation?